today's main idea, we need to introduce the electric flux, but that will be most likely in the second half of the class, because we still have some material related to the previous class material, right? And you remember where we stopped? We stopped at this slide, right? We introduced the formula or the expression which allows us to find electric field strength created by an infinitely large charged plate or plane or surface, right? So E equals eta. Eta, it's a surface charge density. Again, in the previous class, we introduced all these densities. Surface charge density, it's a, if you take, for example, on this surface, patch 1 meter by 1 meter. So it will be amount of charge in that, on that patch, right? I don't know, 5 coulombs per square meters. And so eta divided by 2 epsilon naught. Epsilon naught is that a universal constant, right? And in this picture, if you have a positively charged plate, you see we have electric field lines. Density of them is exactly the same. So it means that this electrical object gives us a uniform electric field, right? And of course, in real life, we don't have an infinitely large surfaces. But of course, with very good approximation, if, for example, I have a charged surface like this, right? Uniformly charged. If I'm interested in the electric field, for example, at a distance like this, right, from the surface, and if I stay away from the edges of this piece of paper, right, charged paper, with very good approximation, I can use this formula, right? But if I want to know the electric field at this distance, no, that will be a very poor approximation, right? So my answer will be reasonably far away from the actual value of the electric field at this point, because the distance to the surface is comparable to the size of the surface. Of course, right, this formula is going to give us very, very bad results, right? Okay, so, and now, so, next step. Let's introduce a device which, another device or electrical system, right, which allows us to get uniform electric field. So the first electrical system, it's this surface, right? And now let's make slightly more complicated electrical system. So let's assume that we have isolated, positively charged plate. So now we know how we can find electric field strength, right? So electric field lines will be like this, right? It's a uniform field. On this side of the plate, electric field lines will be that way, because you remember electric field lines start on positive charges and end on negative. Okay, let me check your chat. Somebody posted something. Okay, can you hear me? Because Samuel... okay, so then Sam, check your system. On my side, everything seems to be working since students can hear me. Check your settings on the computer or something else. So that's a situation if we have a single plate. And of course, okay, let me bring the slides back forward. Right, and the expression is eta over 2 epsilon naught. If we have a negatively charged surface, again, isolated, negatively charged plate, we will get this picture. So you see now electric field lines are towards the plate, because you remember electric field lines end on negative charges. And of course, electric field strength can be described by exactly the same formula, eta divided by 2 epsilon naught. And so now, absolutely logical step, the next step. What if we take these two isolated plates and bring them closer to each other, very, very close, of course, without touching? Okay, let's do it. Okay, let's do it. So if we bring these two surfaces together, of course, now we will have superposition of these two fields, red field and blue field. Red and blue, it sounds like a Republican contribution and Democratic contribution to the net electric field, right? Okay, so now let's superimpose these two contributions, these two fields, red and blue. Okay, let me start with red. All right, so this electric field line I can draw over here, right? And that one over here. So that one goes through the negatively charged surface. You can say, so how come that it goes through? It's normal. It's sort of like a gravitational field. So here's the table, right? Surface of the table, small one. So there's a gravitational field underneath, there's a gravitational field above, right? So it just goes through the table easily. So the same with the electric field. So it goes through this surface. This positively charged plate creates its own electric field at all points of the space, right? All the way to infinity. Okay. So, and now of course I can draw the rest of the red lines. Okay, so now on top of that, of course, we can draw a blue contribution, blue lines in exactly the same way. But now on this side, yeah, we have this blue. And then, of course, the blue line on this side, of course, will go through the red plate and the rest of the blue contribution. Okay, so now let's superimpose them. Look, on the right side of the system, we have electric fields in the opposite directions, but absolute values are the same. Eta divided by 2 epsilon naught. So these two contributions on the right side of the system, they just brutally cancel each other, giving us a zero net electric field. Exactly the same story will be here on the left side. Again, giving us a zero net electric field. But inside of the plate, okay, inside of this system, of course, these two fields add up each other, right? So electric field will be doubled, right? Okay, so over here, okay, outside, just mathematically, why I'm getting 0, right? So of course it will be just eta over 2 epsilon naught minus eta over 2 epsilon naught. It gives us 0. That's what we have outside of the system. But inside, they add up each other. So inside will be with a plus. And as a result, we have expression for the electric field inside of the system, which we call a parallel plate capacitor, of course, right? The expression is eta, again, it's a surface charge density divided by epsilon naught. So this is the second system which we are going to use a lot and which gives us uniform electric field. So from now on, most of the time, we're going to use these two electrical systems, either a point charge or a parallel plate capacitor. All the time, you'll get sick and tired of these parallel plate capacitors, right? And since it's kind of difficult, okay, too much to write or too much to pronounce it, quite often I abbreviate it as, instead of a parallel plate capacitor, I abbreviate as a PP capacitor. It comes from, if you watched Everybody Loves Raymond, I remember 10 years ago I watched it. And in one of the episodes, Raymond was called in school, in high school, I think, like a PP Raymond. So based on that, I abbreviate as a PP capacitor. All right, to make my life a little bit easier. All right. Okay, so parallel plate capacitor. For a week or so, we will use it just as a system which gives us a uniform electric field. But later on, we will introduce capacitors properly, and we introduce capacitance of this capacitor, but that will be later. For now, it's just a system which gives us a uniform electric field. And again, remember, electric field outside is 0. Electric field is not 0, only between the plates. Okay, so now we have two systems which can give us uniform electric fields, either infinitely large charged surface or a parallel plate capacitor. Guys, be careful, because I've seen in the past, I remember letters from students why I'm not getting the correct answer. Sometimes students, by mistake, use wrong formulas. They can use, for example, this formula, eta divided by 2 epsilon naught, to find electric field inside of the capacitor. Or use this formula to describe electric field over a charged surface. Careful. The difference between them, factor of 2 downstairs. Electric field inside of the capacitor is stronger. Silly mistake, but almost every semester, some students made this mistake. Right. Okay, so now after this, what's next? So now we can start using these electrical systems in problems, right? And let's do it. Let's discuss motion of a charged particle in an electric field. And of course, most of the time we're going to use uniform electric field. I think the first quiz will be probably next week. I will announce it over the weekend. There will be a quiz about this. Right, motion of a charged particle in the electric field. One of the examples is here. You can find it in my notes. This example, you will be able to read by yourself. I'm not going to solve this example. I'm going to solve a different problem, very similar to this one, but different, right? So you'll have two examples to practice. And of course, there will be something similar in your homework. I think one problem. Right. Here, electric field is created by a capacitor, parallel plate capacitor. In the problem which I'm going to solve now, the electric field will be created by an infinitely large charged surface. Okay, so now let me switch to whiteboard and we can look at that example. Problem 23-29. Again, chapter 23, problem 29. Where we have a charged plate, basically infinitely large, right? Charged plate. I drew it. Negatively charged. Surface charge density is given. Okay, absolute value is 2 times 10 to the power minus 6 coulombs per square meter. Negatively charged. Then we take a proton, okay, positively charged particle, and shoot it outside, away from the plate with the initial velocity, a large velocity, right? It's almost like a 2,000 kilometers per second. That's quite a speed, right? All right, and so we need, okay, you know what, before I say what needs to be found, let's discuss what happens to this proton as it travels. First of all, you know what, before even I start discussing what is going to happen to this proton, let me make picture better. What do I mean by that? Let's draw electric field. Electric field lines, right? Because they are one of the essential, electric field is an essential player in this game, right? Okay, so negatively charged particle. I mean, plate. So of course, electric field lines end on this surface. So it means that over here I have to draw something like this, right? So this is, okay, E, right? Okay, I can draw more, and one here, and maybe one there, right? So electric field lines, negatively charged surface, so electric field lines towards the plate. And on this side, of course, I can draw this way. Okay, now it looks better. Then, again, before even I start discussing problem, since we're going to deal with vectors, one-dimensional vectors, but still vectors, let me introduce coordinate system immediately, right? To make me feel better, right? Okay, I will introduce it this way. So that's my x, and I will position origin at the place where the plate is. Okay, and now we can discuss actually the motion of this particle. Okay, in simple words, so what is this proton going to do as it travels away from the plate? Since negatively charged object, positively charged object, of course, they attract. Of course, a proton is going to be attracted towards negatively charged plate, and as a result, a proton is going to decelerate, slowing down. So, and of course, after some distance, it is going to stop for a moment. That will be a turning point, turns around and start traveling towards the plate. So in this problem, we need to find the distance to that turning point. Okay, distance from the surface to the turning point of the proton. So that's the problem. Okay, let me draw the trajectory. Okay, so here it travels this way. This is a turning point, right? let me write something like this. So this is a turning point. Let me ask you, what's the major feature of the turning point? One of the major characteristics of the turning point, of a turning point, any turning point.
Acceleration is 0.
Okay, careful. Acceleration or something else?
Velocity.
Physics 1. Velocity. Acceleration actually will be the largest, most like. No, acceleration or not the largest. Sorry, the acceleration will be constant. What I just said, forget it. Don't tell it anyone. Right? It was completely stupid what I said. Acceleration here will be constant, not the largest. Right? I said without thinking. Right? No, acceleration is not going to be 0. Right? Acceleration will be constant. Right? And not 0. Velocity will be 0. Yeah. That's the basically major characteristic of a point, of a turning point. Okay, so now let me show it here. V equals to 0. Okay, and let me show that what we need to find. So this is a point X which needs to be found. Right? So we need to find, okay, let me write it here, X, turning point. What else needs to be added here? It looks like I gave you everything. I gave you all my heart, right? Yeah, nothing else is given in the problem. Okay, so now it means that let's start solving. Some of you probably will capable of started solving this problem because it's actually very similar to the problems which you solved in physics 1. But you know what? Before we start actually solving it, before we start going through all those gory details, I want to discuss the strategy of this problem, sort of create like a skeleton of the solution. And once you have a skeleton, then when we start solving, yeah, we can put those pieces of meat. It sounds like a Frankenstein's creature, right? But anyway, it's very useful to see the structure of the solution. Okay, let me create that skeleton of this problem. And usually I start from the end. What do we need to find at the end? We need to find position of the proton at the turning point. So the final point will be, we need to find X, right? So now, what do we need to know in order to find X? X, actually, it's position, right? It's one of the kinematic quantities, kinematic parameters. From physics 1, you remember, there are sort of 3 categories of those kinematic quantities. The upper level, usually there are like 3 levels of these kinematic quantities. The upper level, it's a position, distance, displacement of objects, right? So it's a first level, sort of like a position level. Then, if you differentiate this position level, you will be able to dive deeper to the velocity level. Average velocity, instantaneous velocity, that's all on that level, right? Again, it's one of the kinematic quantities. And if you want to, and you can also dive even deeper if you differentiate velocities, you will get to the acceleration level. So these 3 levels of kinematic parameters, and in physics 1, you played with them a lot. And of course, everywhere time is involved also, right? And in order to predict some of those kinematic parameters in the future and so on, right, which equations you used in physics 1? Kinematic equations. Of course, there are restrictions on those kinematic equations. Acceleration must be constant. So in those kinematic equations, acceleration plays a major role. And in order to predict, for example, position, you need to know acceleration. In order to predict the velocity of the system in the future, you also need to know acceleration. So here, in order to predict X is basically future of the system at the turning point, right? We're like a fortune teller trying to predict the position of the system. Or future tellers, right? So in order to predict X, in order to calculate X, we need to know acceleration. And then kinematic equations, one of the kinematic equations can help us to complete this step, to make this step. So here I will write acceleration, A. And of course, this step can be completed using kinematic equations. Which one we will see when we start discussing the problem. Right now, again, as I said, we're discussing sort of like a skeleton of the solution. Okay, so now the step before this, what do we need to know in order to get information about the acceleration? Yesterday, we already discussed something like that, right? We need to know something about, not something, we need to know, we need to have information about the force. In this case, of course, electric force, because that's the only force acting. Gravity, of course, we can forget. Gravity in this case will be way, way smaller, right? So we need to have information about the force, and of course, that will be electric force. And Newton's second law will allow us to make this step. So F equals ma. Okay, so now the step before this. So what do we need to know in order to get information about the electric force? Electric field, right? And we can use that fundamental equation for the electric force, which we introduced yesterday or a couple of classes ago. Okay, I forgot, but recently, right? E. So we need to know information about the electric field, and of course, F equals QE. Okay, let me write in the vector form, and maybe I can put vectors over here. All right. So that's it. And of course, information about the electric field, yeah, we can get from the problem. So that is the skeleton of the solution. Let me frame it even, right? So, and now we just need to go through this carefully and solve the problem. The example which I showed to you in my slides also solved according to similar skeleton, but over here at the end, I think you will have to find time, right? Sometimes time can be here, sometimes velocity needs to be found at the end, right? But solution structure of this skeleton are very, very similar, almost identical. Okay, so now we can start going through all these steps. So first, we need to get information about the electric field. Just now we derived, actually yesterday we derived expression for the electric field created by an infinitely large charged surface, right? And you know what? We wrote in the slides sort of expression for the strength, electric field strength. Here I want to keep everything in the vector form. And in a few minutes I will explain why. Because I want to get the right sign next to the acceleration. Okay? So I want to write electric field in a vector form. So electric field vector, you see, will be, okay, surface charge density is negative. I don't want to use that minus over here. I want to get the right expression for the electric field just by looking at the picture. So I'm going to put an absolute value sign on eta. Right? So I'm going to write something like this. Absolute value of eta divided by 2 times epsilon naught. Just basically I use the formula which we derived in the previous class, right? You remember. But since it's a vector, I need to show a direction. What's the direction of the electric field? So electric field on this side of the plate points that way, negative x direction. Of course, electric field on that side of the plate points in the positive x direction. Since proton travels here, electric field points in the negative x direction. So now let me show that direction over here. I can put just minus I hat. You remember I hat? It's a unit vector which has a length of 1. Pointing in the positive x direction. You remember I hat, j hat, k hat. I hat for x direction, j hat for positive y direction, and k hat for positive z direction. So this I hat points in the positive x direction. So I can write my electric field like this. Okay, so right now we are at this point. So now let's move to the electric force. And charge Q, it's a proton, It's positive, so no troubles from there, no additional minuses. So now at the second step, I can write that electric force equals Q times E, right? And in the example in my slides, there is an electron over there. So of course there will be additional minus from the sign of the charge. But here it's a proton, everything is fine. Okay, I don't like my equal sign. So it will be just Q absolute value of the density divided by 2 times epsilon naught, and in minus I had direction. So electric force points in the negative x direction. Yeah, that's true, right? Because this is electric force, because of course this proton is attracted to the negatively charged plate, and the force must be that way. So now we got it mathematically. So yeah, that force must be in that direction. So now we're at this point, and now in order to get acceleration, we need to use Newton's second law. Okay, I immediately write down A. A equals electric force divided by the mass of the proton. Okay, of course, we assume that mass of the proton, charge of the proton, basically universal constants. You can open the book and you can see those numbers. It's under the cover of the book, and inside there are set of those constants. So you can Google it. Those constants are the same everywhere. All right, so now we just need to add mass over here. Mass of the proton, again, is, I assume that we know, right? Q eta divided by 2m times epsilon naught, and in the negative x direction. So pretty much now I can explain why I wanted to write everything in the vector form, because now I can see that my acceleration, you see, is negative in the negative x direction. It will give us a deceleration. It points that way, but object moves this way, opposite direction, so object decelerates, right? So we need to use that minus sign in our kinematic equations. So pretty much because of that, I wrote down in the vector form so that I have that minus for the kinematic equations. Okay, so now we're at this point, and now we need to make a decision which kinematic equation to use. Okay, let me remind you those kinematic equations. If you forgot about them, there are 3 of them. Let me quickly write them down over here, maybe. And then I will continue my solution over there, right? I just need to make a decision which equation is the best. So the first equation allows us to predict future of the velocity. So v equals v naught plus at. It can be minus at if acceleration is negative. That's why I wanted to see minus explicitly, right? So this formula allows us to predict future of the velocity. This is the past of the velocity, and then this is the future. Then second equation allows us to predict position. Again, this is the future. Position of the system in the future. This is in the past, right? Initial position, right? And again, acceleration. If it's acceleration negative, then of course you use either negative acceleration or put minus in front, right? And okay, pretty much these equations usually can be enough, right? But there are situations, there are problems where information about time is not given, and the question is not about time. And of course, yeah, you can combine these equations, right, during the solution, but it's kind of tedious, right? So as a result, people just combine these equations immediately, eliminated t, time, and introduce the third equation, which is I usually call like no time equation, because that's the major feature of that kinematic equations. So no time equation looks like this. V squared is basically sort of future velocity, right? Velocity in the future of the system equals v naught squared plus 2a and x. Okay, let me write just delta x. Delta x. So these are kinematic equations. again, predicts future of velocity, predict future of position, and then just no time equation. You see the major feature, there is no time. Here, there is a time, there is time. Right. So now, which equation is the best for this problem? Again, yeah, you can just grab both of these equations and you can solve the problem. But in this case, if you use these two equations, you will have to make several steps in order to solve the problem. But since in our problem, there is no information about time, the question is not about finding time. We need to find x. It's usually clear indication that most likely the best equation will be the last one, where there is no time. So in this case, yeah, if we use this equation, we can find position x in one step. All right. Okay, so we're going to use this equation. So let me write it down over here. Before, I should have asked a few minutes ago. Can you justify that we can use these kinematic equations? Under which condition kinematic equations can be used? It's very important. Every time usually bug students, right? Can we use kinematic equations in this case? Or cannot we? Or why? What's the major, okay, what do we have to check before we can start using kinematic equations? It's physics 1. Kinematic
Constant
equations.
acceleration.
Yeah, I see also in the chat. Yeah, thank you. Yeah, exactly. Acceleration must be constant. And in our case, acceleration is constant. Q is constant, eta constant, everything is constant. Acceleration is constant, so kinematic equations can be legitimately used. Right, so let me write, so it's equal to constant and kinematic equations can be used. Okay, so I will use the last one. So it will be v squared equals v naught squared plus, okay, I will use plus, but I will remember that my acceleration is negative. So when I plug expression for the acceleration, I will show that minus explicitly, right? 2a, so here acceleration is effectively negative. And delta x, I will write explicitly. Of course, delta x, it's a final position minus initial position. Okay, so now let's simplify this equation immediately because we know plenty of information about the system now. Final velocity. What's the value of final velocity? Our final point, you know what, I should write. So this is our final point, right? And this is our initial point. So it starts here, ends there. Final velocity, 0. We can dump this left-hand side. Then initial velocity is not 0. Acceleration we just found. Final position, that's our unknown, x naught. Proton starts at the origin. This is also 0. And that's our unknown. Right. Okay, so the final push, the final step. So this is our unknown, so we need to move terms around. So x is equal. So this goes to that side with minus, so we'll have minus v naught squared divided by 2 times a. And there's no reason to panic because of this minus, because you remember our acceleration is negative. So let me write down the expression for the acceleration with minus sign. So it will be minus v naught squared divided by 2. Again, it's so difficult to write at the bottom of the whiteboard. Divided by this with minus. And of course, now vector sign I will drop. Right. 2, this minus q, absolute value of eta, and divided by 2. Can you see? Yeah, it's there. M epsilon naught. Right. Minus and minus will disappear. 2 cancels 2. And as a result, this m epsilon naught will go to numerator. So it will be m epsilon naught v naught squared divided by q and absolute value of the surface charge density. mass of the proton. Don't use by mistake mass of an electron, right? And charge, yeah, charge is the same, right, as an electron, but positive. Okay, so if you plug numbers, which of course I'm not going to do, you will end up with 0.18 meters. So which is 18 centimeters. 18 centimeters. Actually, it's a quite an deceleration. You see, initial velocity at this point is 2000 kilometers per second, a gigantic velocity, right, for our life. But for elementary particles, that's normal, their normal life. So 2000 kilometers per second, and after 18 centimeters, probably over this distance, it stops. It's a gigantic acceleration, right? Okay, so that's the problem. Again, as I said in my slides, a very similar problem you can read by yourself. After this, you should be able to understand, except for in that problem, you need to find time. There will be quiz next week, a little bit more complicated than this, right? And that's why I give usually like a day or day and a half, right? That's how I run quizzes.
May I ask a question real quick?
Oh, can you repeat?
Can you hear me?
Yeah.
Oh, I have two questions. One, I thought that kinematic equations could only be used for linear motion. Is that true?
Okay,
Well,
this is
it
the
is,
linear
but
motion.
I thought that
This
was
is the
like stipulation.
you
then
mean because I first the particle move here and then it's slightly below?
No, I thought that's
No.
like, well, you asked when can you use kinematic equations, and I thought it was only for linear motion. These specific.
To some extent it's true, because yeah, when you have two-dimensional motion, you usually decompose that motion into two types of motion, two linear motions. You remember in
Yeah.
physics 1, right, when you have parabolic motion, and every time we discussed it, what motion along the x-axis and motion along the y-axis. Yeah, and then you can use kinematic equations twice, for the x motion and for the y motion. Yeah.
And my second question, I
But
think
again,
that
that's not the major feature. The major feature, we derive them when acceleration is constant. If acceleration is not constant, it will be illegal to use them. If acceleration is not constant, you will have to just you will have to integrate Newton's second law, which is basically second order differential equation.
Thank you. My second question, I think I'm just like really off the game today. How do you find Q?
As I said, in this case, since we're working with a proton, okay, the proton,
it's the
universal constant.
okay.
God
All right.
created these particles in this way and assigned the charge, right? So we just measured it and
Okay, sorry.
tabulated it. Yeah.
Thank you.
Usually we assume that all this mass of the proton or electron charges are known, unless problem asks, okay, find the charge, right? So for whatever reasons, right? Yeah, those are universal constants.
Okay, thank you so much. Sorry.
Yeah. No, it's so great to talk to people and hear human voices, right? So thank you. Right. So now after this, let me switch back to slides, and we will continue with the major goal of today's class, to introduce new quantity. Okay, everything seems to be working. Okay, so this is the example of what I was talking about, and you see the skeleton of the solution is very, very similar, except for at the end, now instead of x we have time. You can find time. Sometimes it can be velocity, right? But again, solutions are very similar. Okay, so next. Okay, guys, now slowly we start moving, or starting, moving towards the next fundamental law. one of the most fundamental laws in physics. We start moving towards what is called Gauss's law. It's actually one of the equations in a set of Maxwell's equations. Coulomb's law actually is not in that set of equations. Gauss's law is, right? And you know what? Before we start introducing Gauss's law, let me give you the idea behind the Gauss's law, the way I see it, right? And that's why I created this cartoonish picture, right? So, have you ever played Yankee Swap? Actually, I'm sure that you all played, since even I played it a couple of times, and I'm usually the last one who does anything new, right? So, how does it work in a Yankee Swap? So, there is a table, right, filled with boxes, right, and inside of each box there is some present gift, right, some valuable thing, right, and you go to the desk, to the table, right, and so what's your goal? Of course, you want to get the best present, the best gift possible, right? And you grab the box, any box, right? And usually you start estimating what can be inside, sort of predicting, guessing, estimating what is inside, because you cannot look inside, right? That's not possible, right? What is available to you? Only the surface of the box. So you can do whatever you feel with the surface of the box, but of course you cannot open it up and see what is inside. So as a result, you explore the surface, what is available on the surface of the box, right? You can touch it, right? You can weight it, you can shake it, you can smell it, kiss it, whatever you feel like doing in order to predict, to guess what is inside, right? Again, you explore the surface in order to guess, predict what is inside. In the Gauss's law, is a very similar. There is a very similar idea behind Gauss's law. We will have some. So you know what? Let me flip a few slides, right? So yeah, sort of. Yeah, I compare with Yankee Swap. So in the Gauss's law, we'll have something similar. We will have some boxes, right? And we will explore the surface in order to predict, explore the surface in terms of electric field, in order to predict the amount of charge inside of the box, right? Even now, without knowing Gauss's law, I can give you a couple of examples in order to show that there is a connection between electric field on the surface of the box and the charge inside. For example, I took this picture from the book, right? So let's say this is sort of like a black box and we don't see what is inside, right? But what we can do, we can just grab a probe charge, small positive probe charge, and map a field around this box. And let's say we got this electric field. So you see electric field lines are getting out of the box. Can you tell me immediately some information about the net charge inside of this box? It should be trivial, right? I'm sure that all of you already can tell me that the net charge inside of this box is positive, because you remember electric field lines, they start on positive charges and either go to infinity or end on the negative charge. Since electric field lines are getting out, it means that inside there is a net positive charge. So you see, there must be a relationship between the electric field information about the electric field on the surface and the net charge inside, even without knowing Gauss's law. But of course, Gauss's law gives us much deeper relationship or information about the relationship between electric field on the surface and the amount of charge inside. Right? It's like in Yankee Swap. We explore the surface, right, in order to predict the gift inside. Or this example, right, again, basically the same story, but now let's say electric field lines are getting into the box. Yeah, we can immediately tell, okay, yeah, it means that inside of this box there is a net negative charge, right? But of course, as I said, Gauss's law gives us a much deeper understanding between the relationship between electric field on the surface and the amount of charge inside. Okay, now let me state sort of Gauss's law in words, because, okay, so Gauss's law basically allows us to connect what? It allows us to connect number of electric field lines crossing the box, crossing the surface. This is my Boston Marathon mug from my running days, right? It's not very practical, but looks cool, all right? So it allows us to connect number of electric field lines crossing the box, crossing the surface, and the amount of charge inside of this box. Again, it allows us to connect number of electric field lines crossing the surface and the total amount of charge inside of the box. Which part of this statement is the most confusing for you? I can tell you what is most confusing for me. If I were in your shoes right now and I hear about this law for the first time, for me it would be, you said number of electric field lines crossing the surface? What is that? Because I can draw one electric field line, or I can draw 100 or 1,000. So it's so obscure, so not well defined. What do you mean by number of electric field lines crossing the surface? Right now it's completely not defined, right, and so obscure. Right? So we need, in order to introduce Gauss's law, so the first thing we need to learn how to count electric field lines crossing a surface. We need to introduce a completely new tool to do that, because right now we have no idea what that is. For most of you, it's you hear about this for the first time. And thanks God, thanks to mathematicians, they introduced this tool for us. It's usually like work like this all the time. Mathematicians introduce some new tools and then physicists start applying them to the real world, right? Sometimes those mathematical tools are useful, sometimes not, but that's how it works. They are basically mathematicians like a tool makers for physicists, right? Okay, all right, so 10 seconds. So now we need to introduce a new tool, and the name of that tool, which allows us to count number of electric field lines crossing a surface, and the name of that tool is the electric flux. So now we realize that right now we're not ready to introduce Gauss's law, because very important quantity is missing. We don't have that quantity. So as a result, we need to push introduction of the Gauss's law till Monday, because right now we're not ready. And today we're going to spend the whole class introducing the electric flux. Again, physical meaning of the electric flux, number of electric field lines crossing any surface. All right? And whenever I pronounce flux, right, it reminds me immediately, I guess you know what, right? That movie, Back to the Future, Flux Capacitor, right, of Doc Brown, Flux Capacitor. It's a good one, a good movie, right? All right, I watched it many, many times, right? Okay, so let's have a break, 10 minutes, right, so till 9, and then, yeah, we will spend the rest of the class introducing the electric flux. It's a very important quantity, and then in a few weeks, we will introduce in a similar way magnetic flux. Idea will be very, very similar, except for we will replace the word electric field with the magnetic field, and that's it. The rest will be very similar. As a result, then in the future, we will spend much, much less time discussing magnetic flux, because ideas are very similar. But today, we're introducing electric flux, idea of the flux for the first time, and we will spend pretty much 1.5 classes discussing it. Right. Okay, so let's have a break, and I will sit here waiting for your questions if you have any, and then we'll continue. Okay, so let's continue with idea of the electric flux. flux. Very important quantity. Okay, let me bring slides forward. And okay, so first we need to understand which quantity must be involved in the definition of the electric flux. And yeah, I took this idea from the book, right? So where idea of the flux is compared with the amount of air crossing certain surface, certain loop. Here the loop is rectangular. I don't have a rectangular loop, so I use my loop circular. And right now, actually, fan is blowing air on me, sort of to make me feel better, right? So so air flies this way, right? And so now I want to know which parameters must be involved in order to describe amount of air per unit second, per unit time, per unit time crossing a loop. Right, amount of air, maybe 5 liters per second, 3 liters. Again, amount of air per unit time crossing this loop. So which parameters must be involved, which quantities? Of course, first of all, it depends, amount of air crossing the surface depends on how fast these molecules fly. The faster they fly, the larger amount of air is going to cross this surface, again, per unit time, per second, for example, right? If molecules just don't fly, don't move, right, velocity is 0, of course, then none of them will be able to cross this surface, and the amount of air will be 0, right? So first of all, the field must be involved. The stronger the field, the larger the electric flux. So the first quantity which must be involved in the definition of the electric flux, it's the electric field. Makes sense. Second parameter is more than obvious. The larger area of the loop, of course, the larger amount of air can cross, right? And the same with the electric flux. The larger the loop, the area of the loop, the larger the value of the electric flux, right? So two parameters are electric field and the electric field and the area of the surface. Every time I'm trying to watch which fingers I use, right, so that I wouldn't show anything, right? Sometimes it happens by accident. Then the last parameter. Of course, amount of air crossing the surface depends also on the sort of orientation of this loop. Right, if for example, if I start, if I keep the loop, if I position the loop like this vertical, right, and air flows this way, of course, in this case, I will have the largest amount of air crossing the surface. But once I start tilting it, of course, the amount of air starts going down, becomes smaller and smaller and smaller. And when my loop is horizontal, of course, molecules will fly parallel to the surface of the loop, and none of them will be able to cross this loop, right? And the amount of air will be 0, and the same story with the electric flux. So also, there must be some angle describing orientation of the loop must be involved in the definition of the electric flux. Again, so 3 parameters: electric field, area of the surface of the loop, and some angle which describes orientation, right? Okay, and now we're almost ready to introduce this new tool. But again, we need to hold for one additional slide. Now we need to introduce again, now before we introduce the idea of the actual definition of the flux, we need to introduce a very strange vector. Not natural, kind of artificially introduced, right? But useful in terms of it simplifies notation of the flux, sort of the structure of the flux, right? So we can write it in simpler form, right? It's not that we desperately need this area vector, but it's very useful, right? Okay, so let's introduce this area vector. And we're going to use this area vector for, from time to time, actually, I would say even often, right? At a certain point, you will get used to this area vector. So, by definition, it's again just a tool which mathematicians prepared for us, right? Or for themselves, and we just started using it, right, stole from them, right? Anyway, so if you have some surface, for example, like this loop, right, the area vector by definition is perpendicular to the surface. No questions why and blah blah. No, just by definition, that's how the area vector is introduced in order to simplify notations of the electric flux. So area vector is perpendicular to the surface all the time. Perpendicular, it means that you can point it this way or this way in the opposite direction. There are no restrictions. Right now, you can point it this way, that way, but it must be perpendicular to the surface. It's the first part. The second part, magnitude of this vector. The magnitude of this vector equals to the area of the surface. Two parts, it's perpendicular and magnitude equals to the area. That's it. Very strange vector. Okay, right, so for example, okay, this is basically the definition, right? If you have, for example, a rectangular loop, yeah, it's perpendicular and magnitude equals to the area. And of course, in this case, you can also introduce area vector pointing downward. Nothing wrong with that. Right now, there are no restrictions. You have a freedom for now. In a few slides, I will start practicing my dictatorship skills and I will take that freedom away from you, right? But for now, enjoy this freedom. You can use point area vector upward or downward. Yeah, you have that freedom. And I will justify why I will take away that freedom from you, but that will be later. Or if you have, for example, this circular surface, area vector, you can point it that way. Okay, that way, right? Or opposite direction. Again, you have a freedom. And again, magnitude must be equal to the area of this surface. And finally, now we can finally introduce the definition of the electric flux, the formula, right? We're going to introduce sort of several expressions for the electric flux for for systems with different complexity. It's basically the same definition, but let me introduce first for the simplest possible case. Let me give you expression formula for the simplest possible situation. What do I mean by situation? Situation, it means that we need to have some surface and we need to have electric field. The simplest possible electric field, form of the electric field. Uniform, right? Uniform electric field. Simplest possible surface. Flat one. Flat surface. So let's first write down the expression for the electric flux for a uniform electric field and the flat surface. Okay, uniform electric field, you see density of lines, electric field lines approximately the same, and a flat surface. Okay, for example, like this. Again, every time in order to introduce the electric flux, you need to have what? Electric field and the surface. Because again, the electric field, it's a number of electric field lines crossing the surface. Or a surface in general, right? So for this simplest situation, mathematicians introduce electric flux in this way. All right, yeah, of course we can draw area vector, like since we just introduced it. Okay, I pointed in that direction, sort of in the direction of the electric field. All right, this will be the angle between these two vectors, right? Electric field and the area vector. And so now, electric flux is just a dot product or scalar product of the electric field and the area vector. And the symbol which we use for the electric flux, capital phi, Greek letter phi, phi with subscript e, because it's an electric flux. That's why we use subscript e. When we introduce the magnetic flux, there will be subscript m. M stands for magnetic, E for electric. Dot product or scalar product. And you see, basically because we introduced this area vector, so this expression looks so simple. Because we introduced this area vector, we can write expression as the dot product. So basically that's why area vector was needed. So we're going to use this formula from time to time, right? Okay, dot product, scalar product. Do you remember it from physics 1? You used it to introduce the idea of work done by some force and somewhere else, I think. But anyway, so at this point, you should be familiar with the scalar product, right? So in the scalar product, inputs, you have two vectors, in this case, E and A. As an output, you have a number. Flux, it's a number of electric field lines crossing the surface, right? And of course, explicitly, you can write it in which way? First option, magnitude of electric field, magnitude of the area vector, times cosine of angle between these two vectors. Okay, now, guys, who remembers how can we find the correct angle between two vectors? It's a place where students made lots of mistakes. Let me remind you where my markers are here. Okay, so how can we find this correct angle theta? The rule is this. Let's say you have two vectors, right? And you want to find the, and you know what, the green marker is a bad choice because green screen effect removes it. Right. Okay, red and black. Okay, yeah, it's better. So let's say they are positioned like this. So what do you need to do in order to find the correct angle? You need to position this vector, tails of these vectors at the same point, like this. You can say, how come that you move vectors? You remember, according to the vector algebra, if you have a vector, you can move it anywhere you want if you preserve its length and direction. If, for example, first I have a vector over here, I can grab it, again, preserving magnitude and direction, and I can position over here or over there. I can position anywhere I want, and it will be still the same vector. But direction and length of this vector must be the same. So that's why if I have vectors like this, right, yeah, I can easily bring them to the same point. Tails of these vectors to the same point. And now this angle, which is less than 180 degrees, is the correct angle between these two vectors. That's how we should find the correct angle between two vectors. That's how we should find theta. So it's one way of finding dot product. The second way of finding dot product, if you have vectors presented in a component form, what do you do in order to find dot product? You just multiply corresponding components, x components, then multiply y components, then multiply z components, and add these three products up. So ex ax plus ey ay plus e sub z a sub z, right? So that's how we can find dot product. Okay, so we're going to practice this formula in a couple of problems. So now, next, a few questions for you. We need to practice with this angle, with this flux, because yeah, in the future, when we introduce magnetic flux, all this stuff will be needed. We will recall one more time. So the first question, and actually, yeah, let's poll it. It's in the chat. Just scroll it up slightly. There are two clicker questions. This is number one, and today is July 9th, right? So the conceptual test 1, July 9th, right? So what do we have here? We need to find the information. We need to get flux, electric flux. So we have surface. You see it's flat, 2 by 2. It's a square surface. And uniform electric field. Electric field strength is over here, 100 newtons per coulomb. Right? So we have uniform field, flat surface. So this formula can be used. So what's the value of the flux? Very simple question. Right, so but first I want to see your answers, right? Try it. I will give you like 20 seconds. It doesn't need more than that. Right. Okay. Number of answers is not growing anymore. So then it means that I need to discuss. Okay, the question is quite simple, right? Yeah, we can use this formula, and we need, okay, electric field strength, yeah, it's over there, it's given, right? Area of the surface, again, basically it's given for square meters. So this factor will be E times A will be 400. We need to understand the angle. What's the value of the angle? At this point, at the very beginning, lots of students made a mistake, because they look at the picture and they see, electric field lines are perpendicular to the surface. It means the angle is 90 degrees. No. Because you remember in the previous slide, we introduced angle as the angle between the area vector and the electric field. Area vector is perpendicular to the surface. So I can, okay, let me bring the slides again forward. So the area vector, again, I have a freedom. I can point it this way or that way, but of course it's better to point it in the direction of the electric field. In that case, flux will be positive, right? So area vector, let's say that way, electric field also the same direction. So two parallel vectors. In this case, the angle is 0 degrees. The angle between two parallel vectors is 0. In this case, it's not 90 degrees. At the very beginning, quite a few students made this mistake, right? It's theta is the angle between the area vector and the electric field vector, right? So in this case, it is 0, and cosine of 0 is 1. Cosine of 0 is 1, and as a result, here we have 400 times 1, so the flux is 400 newtons times meter squared times second. Yes, speaking of units, so we just introduced new quantity, and for the electric field flux, there is no special unit. And again, speaking of discrimination, in a couple of weeks, okay, maybe more, we will introduce magnetic flux, and there will be special unit. Again, pure discrimination between quantities. And again, I will justify it because magnetic flux is used much often because it is involved in the electric current production. But electric flux, no. Right. So as a result, since not many people in everyday life use it, so there is no point of piling up new special units. Right. So whatever you see in the formula, so newtons divided by coulomb times meter squared, right? So the answer is, of course, 400. Right. Okay, the next question I'm not going to poll. I just want to discuss. You will think for a second, then I will discuss, and then the next question, I will poll. So basically the same situation, but now I turned that flat surface by 90 degrees. So now you see the surface is horizontal. What's the value of the flux? Just think quickly for yourself without polling it. You see, I wrote no polling. Right. So what will be the flux? You can think maybe, use the formula. And also, can you think conceptually? Can you justify your answer conceptually? I'll give you like 5 seconds, right? And then I will give you my reasoning. Okay, first, you know what? I want to discuss it conceptually without getting into numbers. In order to explain the answer, we need to remember the meaning of the electric flux. It's a number of electric field lines crossing a surface. So in this case, the surface is horizontal, and the electric field lines are also horizontal. So in this case, these lines just physically cannot cross the surface because they're parallel to the surface. So number of electric field lines crossing the surface is 0. Right? So it's just a simple conceptual explanation. But of course, now, we need to grab this formula and confirm that result. Okay, so again, E times A will be exactly the same because we're dealing with the same electric field and the surface is the same, but orientation of the surface now is different. So as a result, angle is different. And now the angle, the correct angle, again, it's an angle between the area vector and the electric field. So let me draw electric field and the area vector. Area vector, I will pick upward. Again, nothing wrong with pointing it down. It will be equally good. Okay, equally correct, equally good, right? And electric field, that way I just grabbed one of these basically lines and positioned it there. And again, you see I position their tails at the same point. And so the correct angle, of course, is 90 degrees. And cosine of 90 degrees is 0. You all know that, right? Cosine of 90 degrees. So that's mathematical explanation of a zero flux. So as a result, the answer is 0. None of the electric field lines cross this surface. The next question, yeah, that's the second pole. And all right, I'll give you, yeah, a minute. Right. So now, can you apply what we just discussed to find the flux in this situation? So again, the same electric field, the same surface, but now surface is tilted like this. So there is a 20 degrees between the horizontal line and the surface of this plane. Okay, and you see the answers. Right? And of course now actually numbers were not multiplied, so you see basically everything is in front of you. Okay, give it a try. And now, again, you can change your answers, right? If you choose one answer and then you decided to change your mind, okay, just resubmit. Oh, interesting. Unexpected. Oh, somebody liked this question. That's good. All right. There is a quite wide distribution of answers. Usually distribution of answers for this question, okay, based on my experience, it's sort of like a in a bar form, right, during the normal class. It's sort of like a twin towers standing right tall and isolated from anything else. But this time it's a reasonably wide distribution, almost like a Gaussian. Okay, almost everyone responded. A couple of students are missing. Okay, I guess everyone who wanted to answer answered. Okay, so now it's time for me to discuss. Okay, again, so we need to see the area vector, pick the area vector, and again position the tails of electric field vector and area vector at the same point, and so on. So again, we can use still the same formula: flat surface, uniform electric field, right? And I will use this picture, right? So now you see I picked area vector that way. Again, so that it will be somewhat in the direction of the electric field. In that case, electric flux will be positive. Although there is nothing wrong with pointing area vector downward. It will be equally correct. Right? Maybe not the most convenient choice, right? But it will never be wrong. All right. And now we need to understand which is the correct angle. So now once I once I showed area vector, electric field vector, so now you can see that the correct angle is this angle. You see this red, right? This is the correct angle. And this angle 20 degrees is not correct. 20 degrees, why is it 70 degrees over there? Because if I drew this line, you see this black line, which lies in this surface, right? If I drew this line, then this angle 20 degrees and that angle, this angle, will be also 20 degrees. And this angle 20 degrees complement this angle to 90 degrees, right? So as a result, this angle is 70 degrees. And this 70 degrees is the correct angle that must be used in this formula, all right? So you see tails of both vectors are at the same point, and that is the angle between them. So the correct answer is C, right? I will keep bugging you about how we should, about this rule, how we can find the correct angle between two vectors, because it's a place where lots of mistakes students make. Even graduate students sometimes sort of forget about the rules, this rule, and made mistakes, right? In a graduate level course of classical mechanics, for example, right? I also have to Shake them. Guys, remember that. Okay, so that's the correct answer. Okay, so now we introduce the definition of the electric flux for the simplest possible case: flat surface, uniform electric field. Now we need to make now we need to introduce the formula for a more complicated situation, right? Again, we are preparing the final formula which can be used in the Gauss's law. So we need to make this formula more and more complicated. So the next step: what if you have a surface which is not flat? You know, for example, right? So let's say you have something like this surface, right? Not flat, and field which is not uniform, non-uniform electric field, and area is not flat, curved. For example, like this. I took this picture from the book. So now, how can we find electric flux, the total electric flux through this surface, number of electric field lines crossing this surface? Strictly speaking, what we're going to write down now, it's a calculus 3. But again, we will sort of write down the integral and justify it, but we will never actually take those integrals, right? In calculus 3, you will learn how to take those surface integrals. Right now, we want to write down first surface integral. So how can we write down the integral? Of course, it's like in the example, integration example in the previous lecture. You remember what was our first step in setting up that integral? You remember I told you we need to take infinitesimally small section, and I told you that and then treat it as the point whatever, right? And I told you that that is the first step in any problem where you need to set up an integral. Here it's the same story. First, we need to take something which is infinitesimally small, and since here we're dealing with a surface, we need to take infinitesimally small patch. Basically slice this surface into many patches and take one of this patch. You see this one. This is our infinitesimally small patch of area dA. I don't know why book uses this delta. It looks too complicated. No, dA would be fine, right? So dA and electric field E. So now, since this is infinitesimally small patch, I can make two approximations. The first one, so first, yeah, we divide it. So first I can claim that that patch is essentially flat. You can say, how come? Why not? I mean, how come, right? Or if I, for example, compare it with, for example, my room, right? I can claim, since my room on the surface of the Earth is very small, like infinitesimally small, I can say that with a very good approximation, I can treat the surface of my room as being flat. Although if I tell that story to, I know, people in International Space Station, they can start laughing at me. How come that you cannot claim your surface to be flat because it is on the spherical surface. I cannot get the ball out of my mug got stuck. Right. Okay. Because they can say, come on, you are on a spherical surface. Your room surface of your room cannot be flat. But since it's so damn small, infinitesimally small, so I can claim in that limit with a very good approximation, extremely good approximation, I can treat my room as being flat. Although if I looked at the room of my neighbors, yeah, for them it will be also flat, but slightly tilted relative to mine. So mine is flat, theirs flat, but slightly tilted to mine. The neighbors of those neighbors will be also flat, but slightly tilted, right? As a result, all these small, flat, tilted surfaces finally can create the whole spherical surface. So the point is, since it's so damn small, we can treat it as essentially as being flat. Okay, first approximation. Then second, what about electric field? Although electric field overall is not uniform, right? It keeps changing from place to place. It's sort of, it changes. Again, let's compare with the example on the surface of the Earth, right? Of course, you know gravitational field changes, right? If you go to the mountains, it will be different number. If you go to closer to the equator, it will be different number. If you go to the pole, it will be slightly different number. So gravitational field slightly fluctuates over the surface of the Earth, right? So it's not uniform. But again, if I look at my room, I can say it's so small, right? Again, in comparison with the surface of the Earth. So I can say, since it's so small, I can say that gravitational field in my room is exactly the same at every spot. You can bring the best equipment to measure the gravitational field, and you will, in the world, the best equipment in the world, the most expensive equipment in the world, and you will never be able to see the difference between the gravitational field in that corner and that corner of my room. It will be exactly the same. So I can claim this, I can make a second statement. With extremely good approximation, I can say that in this case, over this small patch, electric field is essentially constant, uniform. So now over this small patch, we have two statements. Electric field is basically constant, uniform, and that piece of and that patch, the surface of that patch is flat. So it means that we can use the formula which we just discussed, which we just used for the flat surface and uniform electric field. So we can use that for this small patch. So we can write flux through that small patch as, where is that? Here. Del d phi, flux through that small patch is that electric field at that patch, which is basically constant, dotted with the area vector dA through that surface, right? So it's a small, infinitesimally small contribution to the net flux from that patch. So now if we want now to get the total flux through the surface, what do we have to do? We just need to keep adding these small patches. So first we consider this patch, there is a small contribution. The next small patch, small contribution to the flux, we keep adding. The next small patch plus small number, next patch plus small number. So you keep moving over this surface and keep adding these small contributions. When you complete this addition, you will end up with with some number, and that what we just did, it's just an integration. Integration is just a very fancy word for adding small contributions to something. In this case, we were adding small fluxes. As a result, we're getting the expression for the next to the net flux, electric flux through this surface. It's an integral. It's of E dot dA. All right. Again, strictly speaking, it's a calculus 3. It's an integration over a surface. Again, it's not trivial integration. You will learn how to do it. But again, in this course, we just need this surface integrals, but we will never actually go through those gory details of integration every time. We will see how we can handle these integrals. We will taking them without actually taking. All right. Okay, so we've made a formula more complicated. Now let's make it even more complicated than this. Again, because we will need the final result in the Gauss's law. I wish we could skip this, but no, we need that for the Gauss's law. So the next step in making this formula more complex, let me ask you this question. Do you know the difference between what is called an open surface and closed surface? Somewhere in geometry, maybe you heard. Most likely, no. Usually students don't know the difference between that. Okay, let me explain the difference between an open and closed surface, because it's important. So if we have a surface like this, it's just a piece of paper, right? So that is our plane. And of course, this plane has two sides, two surfaces. This one and that one, right? Two sides of this surface. So now I'm explaining it in simple words. Of course, you can open the book and there will be fancy definition and fancy description of the differences between these two surfaces, right? I want to explain in simple words. So in this case, if you, let's say, imagine you are some small bug and you travel, you start traveling on this side of this plane, right? When you get to this edge, you can easily, you can start moving on this side. And when you get over here, you can easily get to this side of the surface without breaking actually the surface. So when you can do that, when you can move from one side to the other side without breaking the surface is called an open surface. Open, yeah, you can move from one side to the other one. Open surface. But now let's look at my Boston Marathon mug. And it's closed. Yeah, I can open up and I can close. So now let's do the same test with this mug. So if I start walking again, it has two sides, right? This inner internal surface and external surface, right? So now if I start walking on one side, it doesn't matter how much I walk, I will never be able to get to the other side unless I break the surface. Now once I break the surface, yeah, now basically I open the surface. Now yeah, I can get inside, but I broke the surface now. So this surface is called a closed surface. If you start walking on one side, you will never be able to get to the other side. Closed surface. And that is an open surface, right? I think it's reasonably simple, right? Okay, so now here we discussed an open surface and we wrote down the expression for the electric flux for an open surface. Now we need to adjust this formula for my Boston Marathon mug for closed surface, right? All right, okay, so now next slide, electric flux through a closed surface. Basically, a closed surface, it can be a ball, right, and American football ball, right, soccer ball, right, this mug, right, cube, right, so tons of examples, right, non-uniform electric field, a closed surface. Oh, I used this, drew this, closed surface. And, okay, first of all, before we start actually writing down the formula, now it's time for me. You remember a few minutes ago, okay, 10 minutes ago, I told you that you have a freedom to choose direction of the area vector the way you want. You can position it like this or like that. You have the freedom to choose the direction of the and the direction of the area vector. And now it's time to take that freedom away from you. So for these situations when you have a closed surface and you want to find electric flux, right, there is a convention. Area vector must point toward the outside. So now, yeah, I start practicing my dictatorship skills, right? No freedom in terms of choosing direction of the area vector. And justification explanation is very simple, because the formula which I'm going to present now is used in the Gauss's law, and the Gauss's law is one of the fundamental laws in physics. And in the fundamental law, there must not be any ambiguities that you can pick area vector this way or that way. No, it's bizarre. It must not be there. In universal fundamental law, everything must be well defined, no freedom in choosing this direction or that direction. So that's why this convention is imposed in this part. For the closed surface, area vector must point towards the outside. Period. No discussions, because we are introducing very important law. Make sense? I think so, right? Okay, so now let's assume that this, for example, I just drew in the random directions electric field vector and area vector, of course, towards the outside. You see, dA, 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 and all of them all the time towards the outside, right? And so basically, exactly the same arguments I can give now. So we'll have to slice this surface into small patches, take the small patch, exactly the same arguments, right? And then just integrate now. Instead of an open surface, we will have to integrate over a closed surface. But that fact that we integrate over the closed surface must be somehow shown in the formula, shown in the expression. And mathematicians, thanks to them, right? So lots of useful tools. They introduce, you see this circle in the middle of the integral. integral with a small circle in the middle. That small circle in the middle tells us that integration is done over a closed surface. Right now, I was just staring at the formula. It reminded me, in music, the notes, right? They have some fancy circles, some fancy lines, right? So right now, I just looked at this formula. It reminded me music notes, right? Okay, so that circle in the middle, in this case, indicates that integration is done over a closed surface. So this is the formula for the electric flux through a closed surface. And that's what we need for the Gauss's law. So finally, we got the expression which we need to introduce Gauss's law. All right, so at this point, I'm not going to jump into the Gauss's law. Basically, right now, we are completely ready to introduce it, to discuss it, and start practicing it. But before that, we still have 8 minutes. Let me solve a few problems about electric flux. Because we need to get used to that fact, right? Because for most of you, you hear about the electric flux, or flux in general, for the first time. Of course, you heard the flux word in the movie Back to the Future. But it's just because it's a cool term. It sounds so cool, flux capacitor. Hollywood likes fancy terms because it's easier to sell, right? Right, for geeky guys. All right. Okay, so now we will practice expressions for the electric flux for the simplest possible situation: flat surface, and uniform electric field. All right. Okay, let me switch to the whiteboard, and I prepared 2 problems. Probably we will solve only one problem, and the second problem we will solve on Monday. Again, we will have to just find the electric flux. So again, if you want to find electric flux, there must be a surface, there must be field. Electric field. So let me draw the picture. Probably I will start with the picture. So what is given? So we have flat surface. It's a square, I think. Right? Yeah. Let's say this is A 10 centimeters and B 10 centimeters. Then there is a uniform electric field. Let me draw it like this. So that's our E. And one of the angles is given. This angle is given. Let me draw this line which lies in the surface, in the plane of this surface, surface, yeah. And the angle is 30 degrees. Did I label it? Let me label it. Okay, no. I will just write 30 degrees. So that angle is given. So we need to find, the electric field strength is also given. Yeah. Electric field strength is 200, again, units. There is no special unit, just newtons per coulomb. Right? So we need to find electric flux. So first of all, of course, I need to justify that we can use the formula, the first formula, flat surface, uniform electric field. So yeah, we can use that dot product. So the electric flux equals to the dot product between E and A. But you know what? Before we start solving actually this problem, let me digress for 2 minutes. I already mentioned it in the lecture that there are 2 ways of calculating dot product. Let me remind you about that. So first option of finding the dot product. Okay, let me write first. So flux equals absolute value of E, absolute magnitude of A, and times cosine of angle between them. We already practiced it in our clicker questions. The second option, if these two vectors are given in component forms, x, y, z component, right, then you can also calculate flux, and of course you will end up with exactly the same number relative to the first case. So the second option will be EX times AX. Just multiply first X components, then Y components, and add them up. If, of course, there are Z components, you can do the same, right? You remember in maybe in high school or where you first learn about dot products, or maybe in physics 1, there are two ways of finding dot product. And of course, it doesn't matter if you use this or that option, the answer will be, of course, the same. It can be shown mathematically, right? So, which formula is best to use in our case? I think it's more or less obvious, right? Since absolute value of the electric field is given, so it's better to use the first option. Again, if you want, you can use the second, but it will be longer. Finding these components, right, so it will be longer. Easier, the first option. So let me write. So we're going to use the first option, right? So electric flux equals to E, A, and cosine of angle between them. Okay, so electric field is given. Area vector, magnitude of the area vector, it's the area of the surface. We have sizes, so we can find that easily, right? So it will be E times A times B. Okay, let me maybe put them in parentheses to emphasize that this is area vector, right? And now cosine of which angle? Cosine of, okay, on purpose, I'm not writing which angle. Okay, let me hold you for extra 2 minutes. During the, again, normal semesters, normal classes, I usually bug students, right, one by one, several, and quite a few students, they have a habit, right, so they just grab whatever angle is available, right, and start using it. No, sometimes it works. Sometimes it doesn't work. We need to understand which angle must be used, is correct. And you know what? I started discussing it, and now I realize, so in order to discuss which angle is correct, it's better to draw something, to add additional feature to this picture, right? Let's draw area vector on the picture, right? Because without that, without showing it on the picture, it's not convenient to explain. Okay, I will, again, open surface, and I can, of course, I can align area vector either upward or downward. Both options are correct. But of course, I would prefer probably to point it up so that it will be somewhat in the direction of E, so that flux will be positive. So that will be my area vector. So as a result, now we see which angle is correct. You remember the correct angle. You need to position tails of both vectors at the same point. You see area vector that way, electric field that way, and their tails at the same point. So as a result, this angle is the correct angle, right? So let me use blue. So this is angle theta, which we need to use. That 30, I think not, no, 30 degrees. Yeah, right. So that is the correct angle. So over here, let me use even different color. Okay, let me use first theta. No, I will write, so it will be 90 degrees minus 30 degrees. So it's basically theta. Let me show it this way. Okay, because quite a few students, they just grab 30 degrees and use it over there, hoping that it will be correct. Of course, it's better to understand why that or this angle is correct. Okay, so cosine of 30 degrees, it's 1/2. And okay, let me write numbers, at least in this case. So it will be 200 newtons per coulombs times, must be converted, A and B must be converted into meters, 0.1 meter times 0.1 meter times 1/2. So this will be basically 10 to the power of -2. These two zeros will disappear, and these two get cancelled. As a result, we'll get a 1. The answer is 1 newtons times meters squared divided by coulombs. Okay, you see, it's reasonably simple, but we need to practice it a little bit. So on Monday, first thing in the morning, I will solve problem 12. It will be slightly different, but also reasonably simple. It will take us 5 minutes.